Welcome to the deep dive. Today we're tackling some really big questions.
The biggest, maybe?
Yeah, like what is everything actually made of, and how does this whole universe, operate?
They sound simple, don't they? But answering them takes us on this incredible journey.
From the tiniest particles
Things we can barely detect.
all the way out to, well, the entire cosmos.
Exactly.
So our source material for this deep dive is this really thorough analysis looking right at the foundations of the universe.
Yeah. Particles, forces, the big cosmic mysteries, all that good stuff.
And our mission today is basically to give you a shortcut, right? A way to get your head around these fundamental principles.
Understand how the universe plays its very complex quantum game.
And maybe answer some of those questions that seem simple but are actually pretty profound.
Let's do it.
Okay, so one way to think about it maybe is like the universe is a giant game of chess.
Like that. Yeah.
You've got the elementary particles as the pieces, the figures.
And the fundamental laws are the rules they have to follow.
But here's the thing, right? These rules aren't written down anywhere we can just look them up.
No cosmic rule book, unfortunately.
As scientists have to figure them out piece by painful piece.
It's all empirical. Observation, modeling, experimenting, predicting.
And checking if the predictions match reality.
Precisely.
Yeah.
It's sometimes called the shut up and calculate approach.
Huh. Okay.
It means you prioritize the math, the models, the experimental results.
Over just what feels intuitive.
Exactly. Because the quantum world often isn't intuitive. We build models that work, that describe reality.
Right. And the cornerstone model for these particles is the standard model of particle physics.
That's our modern periodic table, yeah. It lists all the known fundamental particles.
And 3 of the 4 big interactions, the forces.
What's amazing, though, is the standard model has, like, 17 fundamental particles listed.
17?
For pretty much everything you see and touch, all the visible matter.
Is made of just 3.
Just 3. The up quark, the down quark. They make atomic nuclei.
And the electron orbiting around them.
That's basically it for everyday stuff.
But you mentioned elusive particles earlier. Neutrinos, they sound interesting.
Oh, they are. Tiny, almost massless, very hard to detect. They're like little ghosts.
Ghosts.
Well, they're released in particle decays, like in the sun's core. And trillions, literally trillions, are zipping through you right now.
Wow. Every second.
Every second. They barely interact with anything. They tell us a lot, though, about how particles work.
So they have heavier versions, too.
They do. Heavier copies, but they're super rare here on Earth.
Okay, so these fundamental particles, are they like tiny little balls? Or points?
That's the common picture, but no, not really.
Yeah.
It's better to think of them as excitations, like splashes.
Splashes. Splashes on what?
On a field. Imagine a vast, smooth surface. This the field stretching everywhere. A particle is a ripple or a splash on that field.
Okay.
And we describe these splashes by their properties: mass, electric charge, and spin.
Spin sounds simple, but I bet it's not just like spinning like a top.
No, not really. It's a quantum thing, an intrinsic angular momentum, like a tiny internal compass needle, sort of. It dictates how they behave.
And these fields, they're not just sitting there.
Not at all. They're constantly rippling like water,
Yeah.
even in what looks like empty space.
So empty space isn't actually empty.
Not in the quantum sense. These ripples create virtual particles.
Virtual.
They pop into existence and disappear again too fast for us to see them directly.
Wow.
So yeah, the vacuum is actually this seething dynamic environment.
Okay, so what are the real particles then?
They're just bigger splashes, ones that get enough energy to stick around, to be observable.
And these splashes, these fields interacting, that's what makes everything. My hand, this desk.
That's it. How these fundamental building blocks combine and interact is what forms everything we see and touch.
Mind-bending.
Yeah.
Okay, so if particles are the chess pieces, what are the rules? The ways they move and interact?
Those are the 4 fundamental interactions or forces. They dictate how particles walk and devour each other, as the source puts it.
Right. There's the strong force, electromagnetic, weak, and gravity.
The 4 fundamental rules of the game.
Let's start with the strong one. The name says it all.
Pretty much. It's the most powerful force, but only over incredibly short distances, like inside an atomic nucleus.
It's the atomic glue.
Exactly. It holds the protons and neutrons together. Remember, they're made of quarks.
Right. Up and down quarks.
And the strong force binds those quarks together, too. The particles carrying this force are called gluons, like glue.
Okay, simple enough. But isn't there something weird about it? Like, it gets stronger if you pull things apart.
Yes. That's the really counterintuitive part. It's not like a magnet getting weaker with distance. It's like rubber bands or
The
springs.
pulling corks apart.
It takes more and more energy. If you pull hard enough, the energy you put in doesn't separate the quarks.
What happens?
It actually creates new quarks. A quark-antiquark pair pops out of the energy.
You're kidding. So you can never get a quark by itself.
Never. It's called quark confinement. It's a direct consequence of EMC squared, really.
Yeah.
Mass from energy.
Wow. So inside protons and neutrons, it's like a constant exchange.
Totally dynamic. Quarks exchanging gluons, pairs popping in and out. It creates this stable structure through constant activity, like an economy, almost.
And without it.
Poof. All atomic nuclei would just fly apart instantly. No atoms, no matter as we know it.
Okay, so strong force. Vital nuclear glue. What about the next one? Electromagnetism. That sounds more familiar.
It definitely shapes our everyday world more obviously. While the strong force holds the nucleus together, electromagnetism is what holds the atom together.
How electrons stick to the nucleus.
Exactly. And it dictates all of chemistry, how atoms bond to form molecules.
And this involves electron shells and something called the Pauli exclusion principle.
Right. Electrons aren't tiny planets orbiting. They're more like probability clouds.
Clouds, okay.
And the Pauli principle basically says no two electrons can be in the exact same state in an atom. So they have to stack up in these layers, or shells.
And that's chemistry, how they fill the shells.
That determines how atoms bond, yeah. Why you get H2O or NaCl. It's all about those electron shells interacting.
And the messenger particle for this force is the photon.
The photon. Massless, travels at the speed of light. It covers the whole electromagnetic spectrum.
Radio waves, microwaves, visible light, X-rays.
All photons, just with different energies. And because they're massless, the electromagnetic force has infinite range.
Okay, get this. When I put my hand on this table, I'm not really touching it.
In a fundamental sense, no. What you feel is solid is the electromagnetic repulsion between the electron clouds in your hand and the electron clouds in the table.
They're pushing each other away via photons.
Exactly. Photons are being exchanged. There's no actual contact between the atoms themselves. Solidity is an illusion created by repulsion.
That is genuinely mind-blowing.
And think about it. Electromagnetism defines so much of our perception. Sight is photons hitting your retina.
Hearing.
Sound waves are air molecules bumping into each other, repelling electromagnetically, transmitting the vibration.
Smell and taste.
Molecules binding to receptors, again, electromagnetic interactions.
Even our thoughts. Brain activity.
Fundamentally, yes. Nerve impulses are electrical signals. It's all electromagnetism at its root. Consciousness itself relies on it.
So the photon is like the universal mediator of our experience.
In so many ways, yes. Even though it's about 100 times weaker than the strong force.
Incredible. Okay, force number 3. The weak interaction. Sounds weak.
Huh. Yeah, the name is a bit unfortunate in terms of its importance. It is incredibly weak on a particle level, like 100 billion times weaker than electromagnetism.
So why is it important?
It's absolutely essential for stars to ignite. Stellar fusion, the process that powers the sun and creates heavier elements.
Like carbon, oxygen, the stuff we're made of.
Exactly. That process starts because the weak interaction can change a proton into a neutron inside a star's core.
How?
Via particles called W bosons. That kicks off the whole chain reaction. Without the weak force, the universe would just be hydrogen and helium, cold and dark. No stars, no planets, no us.
Wow. Okay, so not so weak in its effects. What makes it act so weakly at the particle level?
Its force carriers, the W and Z bosons. Unlike photons and gluons, they are heavy, really heavy.
How heavy?
A W boson is about 80 times heavier than a proton. And the Ws also carry electric charge.
And that heaviness limits their range.
Drastically. They can only act over extremely short distances. That's why the force seems weak. Its arms are incredibly short.
And neutrinos fit in here, right? The introverts.
Perfect description. Neutrinos are super light, no charge, they barely interact. They only feel the weak force and gravity.
So they need to get really close to something to interact via the weak force.
Essentially full contact, yeah, because the W and Z bosons are so massive and short-lived.
And this short range is actually good.
It's crucial. If the weak force had a long range, like electromagnetism, fusion might run rampant. The universe needs that restraint.
Okay. Strong, electromagnetic, weak. That leaves gravity.
Gravity. The paradox.
Paradox. How so?
Well, it obviously governs planets, stars, galaxies, seems immense. But at the level of fundamental forces, it's staggeringly weak.
Right, like you said, I can pick up a paperclip and easily overcome the entire Earth's gravity with my finger.
Exactly. Billions and billions of times weaker than even the weak force at the particle scale.
And Einstein's view was completely different, wasn't it? Not really a force like the others.
Correct. General relativity doesn't describe gravity as particles pulling on each other. It describes it as geometry,
Geometry.
the curvature of space-time itself.
Mm.
Massive objects like the Earth or the Sun literally warp or dent the fabric of space-time around them,
And other objects like planets or falling apples.
are just following straight lines through this curved space-time. They fall because the path itself is curved. Think of it like space-time having invisible road markings guiding things.
So planets aren't pulled by the sun, they're following the curve caused by the sun.
That's the gist of general relativity. It's a geometric theory.
But this creates a problem, right? Trying to mesh this geometric gravity with the quantum world of the other forces.
That is the biggest challenge in fundamental physics today. Marrying general relativity, large scales, with quantum mechanics, small scales.
A search for quantum gravity.
Exactly. Which probably involves finding the particle that carries the gravitational force, the hypothetical graviton. But we haven't found it.
Which leads nicely into another big piece of the puzzle. Mass. Where does it come from? There's a big problem in the standard model initially.
A huge one. The basic equations, the most elegant versions, actually predicted that all fundamental particles should be massless.
But clearly they're not. Electrons have mass, quarks have mass.
Exactly. Experiments showed they absolutely have mass. So how do they get it?
Enter the Higgs field.
Exactly. Peter Higgs and others proposed this idea. What if space isn't empty, but filled with an invisible field everywhere? The Higgs field.
Okay, another field.
And particles acquire mass by interacting with this field. It's like wading through treacle almost.
So the more a particle interacts, the more mass it has.
Precisely. The
Yeah.
analogy is often used. Imagine the field is like water.
Okay,
An electron like a small fish, it slips through pretty easily, low interaction, low mass.
makes sense.
A top quark, though, is like a giant whale. It plows through, interacts strongly with the field, huge resistance.
And therefore huge mass, like 300,000 times the electron's mass.
You got it. And some particles, like photons and gluons,
The force carriers for electromagnetism and the strong force,
they're like needlefish. They just zip through without interacting at all.
which is why they're massless and travel at light speed.
Exactly. The Higgs field gives mass to the particles that interact with it.
And the particle associated with this field, the ripple in the Higgs field, is the Higgs boson.
This is the one. Its discovery about 10 years ago was massive news.
The final piece of the standard model puzzle.
The 17th particle, yeah. It confirmed the whole mechanism. And the Higgs field has this unique property, this sombrero-like potential.
Sombrero-like. Okay, explain that one.
Imagine the energy landscape of the field.
Mhm.
Instead of being lowest at zero, like a bowl, it's got a gump in the middle, and the lowest energy is in a circular trough around it, like the brim of a sombrero hat.
Okay, I can picture that.
When the early universe cooled, the field fell into this trough. Particles interacting with the field in this state gain mass.
And this explains why some particles got mass and others didn't.
Yes, it explains why the W and Z bosons got heavy, giving the weak force its short range, while photons and gluons stayed massless, letting electromagnetism and the strong force behave differently.
So the Higgs field is like the cosmic differentiator.
Beautifully put. It links the quantum world to the tangible reality of mass and force ranges that we see.
Incredible. But even with the Higgs, the standard model isn't the whole story, right? You said it only describes about 5% of the universe.
That's the humbling truth. For all its success, it only accounts for the ordinary matter and energy we know. The other 95%,
Is dark matter and dark energy.
the great unknowns. New physics is definitely needed.
Let's talk about dark matter first. We can't see it, touch it, interact with it. How do we even know it's there?
Purely through gravity. We see its effects on how galaxies rotate, how galaxies cluster together. They move faster than they should if only visible matter was providing the gravity.
So there's extra invisible mass.
A lot of it. Forming these huge invisible halos around galaxies, we think it's some kind of undiscovered elementary particle.
Everywhere. Like in this room.
Probably. Estimates suggest maybe one dark matter particle per coffee cup volume of space, on average. But it doesn't interact with light or normal matter except through gravity. It's invisible scaffolding.
So how on earth do you look for it?
Several ways. One is looking at how light from distant galaxies gets bent as it passes near massive objects' gravitational lensing. Dark matter contributes to that bending. Another is looking for indirect signs, like gamma rays that might be produced if dark matter particles occasionally collide and annihilate each other.
Right.
And then there are direct detection experiments. Huge, ultra-sensitive detectors, usually deep underground to shield from other radiation, waiting for the incredibly rare event of a dark matter particle bumping into a regular atom's nucleus and leaving a tiny trace of energy.
A tough search. Okay, then there's dark energy. Even weirder.
Arguably, yes.
Yeah.
Around 5 billion years ago, something changed. The universe's expansion, which had been slowing down since the Big Bang due to gravity pulling things together.
Started speeding up, accelerating.
Exactly. Discovered by observing very distant Type Ia supernovae, they act like standard candles, letting us measure cosmic distances very accurately.
And they showed things were flying apart faster and faster.
Yep. And whatever's causing this acceleration, we call it dark energy. It makes up the biggest chunk of the universe's energy budget, maybe 68%, 71%.
Wow. And unlike dark matter, which clumps up.
Dark energy seems to be smooth, uniformly distributed everywhere. It acts like anti-gravity, a repulsive force inherent in space itself.
Pushing everything apart.
Right. Which forces us to rethink gravity and the nature of space.
What are the theories?
The leading candidate is the energy of empty space itself, vacuum energy, or Einstein's cosmological constant.
But didn't you say there's a massive problem with that?
Oh, the cosmological constant problem. It's maybe the biggest embarrassment in theoretical physics. Quantum theory predicts a value for this vacuum energy that is, wait for it, about 120 orders of magnitude larger than what we observe.
120 orders of magnitude. That's not just wrong, that's spectacularly wrong.
It's profoundly wrong. It tells us we're missing something absolutely fundamental about how gravity and quantum mechanics connect.
So what else could dark energy be?
Other ideas include quintessence. Maybe it's a new kind of dynamic field that changes over time. Or perhaps Einstein's theory of gravity itself needs modifying on cosmic scales. We just don't know yet.
But it's crucial that it only kicked in late.
Yes, thankfully. It allowed enough time for gravity to pull matter together to form stars and galaxies before this cosmic acceleration really took over and started pushing things apart.
Amazing timing. And speaking of fundamentals, time itself. Einstein totally changed our view of it.
Completely. Newton saw time as absolute, ticking away uniformly everywhere. Einstein showed it's not like that at all.
It's relative.
It's relative. It's interwoven with space into a single fabric space-time.
Right.
And how fast time flows depends on your motion and on how strong gravity is nearby. Time literally runs slower, closer to a massive object, or if you're moving very fast.
So there's no universal now.
Not according to relativity. We each move along our own world line through space-time. The idea of simultaneous events across the universe breaks down. It really messes with our intuition.
It really does. Okay. All these forces, particles, mysteries, it leads to the ultimate goal, right? The grand challenge. Unifying everything.
The holy grail of physics, you could say. Trying to find a single framework, a single set of rules that describes all the forces and particles.
We've had some success before.
Yes, huge success. Unifying electromagnetism and the weak force into the electroweak theory. That was a major triumph.
So the next step is grand unified theories, GUTs.
Right. GUTs try to unify the electroweak force with the strong force. They predict some really interesting things.
Like what?
Like protons eventually decaying, though, over incredibly long timescales. They also predicted that neutrinos should have mass.
Which turned out to be true.
Exactly. So that's a big point in their favor. But there's a catch.
The energy needed.
Yeah. GUTs predict this unification only happens at incredibly high energies, way beyond what our current particle accelerators can reach. Like 10 to the power of 15 GeV or more.
So we can't test them directly.
Not easily. We have to rely on mathematical consistency, indirect evidence from cosmology or astrophysics. It shows our technological limits.
And the biggest hurdle remains.
Gravity, bringing gravity into the quantum fold. General relativity and the standard model just speak different languages, operate on different principles.
Finding the graviton.
That's part of it. Theories like string theory are trying to tackle this.
String theory, where particles aren't points, but tiny vibrating strings.
That's the idea. It's mathematically very complex, very compelling to some, but also incredibly hard to test experimentally so far. It attempts to unify everything, gravity included.
So even if we don't have the final theory of everything yet.
The quest itself is incredibly fruitful. Just trying to unify forces led to predicting neutrino masses, which we then found. The process pushes our understanding forward constantly.
Okay, so let's try and wrap this up. We've seen the universe operates on these fundamental rules, the standard model for particles and forces, general relativity for gravity.
And everything we experience, from boiling water to thinking a thought, traces back to particles interacting through these forces.
With the Higgs field giving mass to many of them and the Higgs boson discovery being a huge confirmation just a decade ago.
But at 95% is still out there, huge questions remain.
How do we unite gravity and quantum mechanics? Does the graviton exist?
Why is there more matter than antimatter? What is dark matter? What is dark energy? That cosmological constant problem isn't going away.
Well, what even is time at the most fundamental level?
We're absolutely in an age of exploration in physics.
Hmm.
So much uncharted territory.
And progress needs, well, big experiments, powerful colliders.
Absolutely. Investment in the tools is crucial.
Yeah.
But just as critical.
Is nurturing the minds, the people thinking about these incredibly hard problems.
Exactly. We need the human intellect, the curiosity, the drive to keep asking those basic, almost childlike questions. What is this place? How did it start? Where is it going?
It feels like every answer just opens up deeper, more fascinating questions.
That's the beauty of science, isn't it? It's this dynamic, ongoing process. Progress relies on both our machines and our minds, our technology and our philosophical drive to understand our place in the cosmos.